Alright, so in this video we'll go over section 4.3, systems of linear equations and problem solving. So what we're going to do in this section is write down systems of equations from word problems and then solve those problems. Alright, so let's see, typically, the most common, the classic problems that we are going to encounter in systems of equations with two equations and two unknowns are those problems involving numbers. So like this example, so the sum of two numbers is 5 and their difference is 11. Find the numbers. Alright, so let's see. It would be a good idea to label the first number and the second number. So the first number, I'm going to call it x, and the second number, I'm going to call it y. So the first sentence right here, it's telling me that the sum of two numbers is 5, and their difference is 11. Okay, so that is, if we write this using a system of equations, we're going to have the following. The sum of two numbers, x plus y, doesn't matter, it's xy, is 5. And their difference, x minus y, notice difference means subtraction or negative sign, equals 11. And that's the system that we would need to solve to get those two numbers. Well, if you observe this system, the easiest method to solve this system of equations is elimination. Notice that the y's have the same coefficient, the invisible one, and opposite in sign. So these are ready to combine and solve the equation. So I'm going to leave this to you. I'm going to help you out, walk you through the hardest part, which is translating the word problems into system of equation. But as an additional exercise, I'll leave it up to you to solve these systems. So let's see. So let's write it down. The preferred method, which is elimination. Elimination is a better choice. All right. So second, another one dealing with numbers. So we have some numbers, two numbers, x and y. First number and second number. So in this case, what are we going to have? X and y. So let's highlight the information. The sum of two numbers is 46. Okay, so the sum of the two numbers is 46. X plus y equals 46. Now, the second piece of information is telling us that twice the first number is subtracted from the second and the result is negative 8. Be careful with the order here. So twice the first is being subtracted from the second. So the second, which is y, minus 2x, because 2x is twice the first, but it's being subtracted from y, which is the second, negative 8. Now be careful when you set up systems of equations, because notice the position, the arrangement do not match when it comes to arrange this variable in columns. So you might want to rewrite the system as x plus y equals 46 and negative 2x plus y equals negative 8. Okay, and in this case, well, there's two ways you can solve this system of equations. You can use substitution by solving for either x or y and then substitute it in the other one, or multiply the first equation by 2 and eliminate x by the method of elimination. Alright, so let's look at another example. So what do we have? Rock and roll. A local rock band played 2 successive nights at a high school gym. The total attendance for both nights was 350 people. but the second night 50 more people attended than the first night. How many attended each night? Well, so we are gonna look for the people that attended the first night and the number of people that attended on the second night. Right? I'm going to use X for the first night and Y for the second night. So the total attendance, so this sentence I'm highlighting in pink, the total attendance for both nights was 350 people. That is, the attendance for the first night plus the attendance for the second night represented by X and Y. The total is 350. Now, in the second night, 50 more people attended than the first one. That is, the second night, which is labeled by Y, equals to 50 more than the first. That is, 50 more, that's plus 50 from the first one, which is X. And in this case, you don't need to move the X to the other side, because over here you might want to just use the substitution method over here and solve this system of equations. Alright, now let's see. Aviation, well, we use systems of equations in aviation here. So in a situation like this, in which a plane travels at a 520 miles per hour with the wind and 400 miles per hour against the wind. They're asking us to find the speed of the plane in still air. Well, how are we going to proceed in this case? So let's see. Let X be the speed of the plane, and let Y be the speed of the wind. Okay, so we're gonna have two situations. The time when we fly with the wind, and against the wind. Alright, so with the wind and against the wind. So this is the picture here. So suppose you take a flight, right? I don't know, let's say from Los Angeles, right? LA, and then you go, I don't know, Miami. Okay, you go from LAX to Miami. So when you go towards the east, you might notice that every time you fly from the west to the east, you go faster than actually coming back from the east to the west. For example, I believe this flight is some 5 hour, and let me just make up some numbers, 5 hours and 30 minutes. The flight back, it could be 6 hours and 10 minutes. It's longer, and this is due to the fact that when we fly in this direction, we go with the wind, which is called a tailwind. That's why we go faster when we go back, due to the way the winds go in our world, on the planet. When we go back with the airplane is fighting against the wind. That makes the flight a bit longer than the flight when you go first and then when you come back. So this is why when we go with the wind, so that's the speed of the plane, and plus the speed of the wind. And then when we go with the flag back against the wind, so because the plane struggles against the wind, it's going to be a subtraction in this case. So speed of the plane minus the speed of the wind. Oops, what am I doing here? Of the wind. Alright, so writing this into a system of equations, as this is simply x plus y equals whatever that speed traveled with the wind, which is 520. And against the wind, well, simply x minus y and whatever that speed is, which is in this case 400. And that's the system of equations we will need to solve. If you look at how it is arranged, elimination would be a good choice to solve this system of equations. All right, let's look at another example. Still another situation in which aviation it comes into play. Well, so with a tailwind, a small plane can fly 300 miles in 2 hours. Against the wind, the same trip took 6 hours. How fast did the plane fly in still air, and how fast was the wind? Alright, so in this case we're going to use the fact from physics, from science, the fact that the velocity equals the distance over time. Or in other more common terms in algebra or in calculus, we use it in a different way. We used rate equals distance over time, and I'm going to use all upper cases just to make our lives easier. So if we arrange this equation, we solve for d, we need to multiply both sides by t to get rate times time equals to distance. Okay, this equation is going to come into play later in the semester, so it's a good idea to start getting used to it. All right, so we're going to use this table to help us set up the system of equations. So we're going to have one column for rate, one column for time, and one column for distance. We know that rate times time equals to distance. Okay, so let's highlight the information that we have. With a tailwind, right? It flies 300 miles in 2 hours. That is a distance of 300 in 2 hours. But that is with tailwind, which in this case that's x plus y, which is the x represents the rate of the plane, the speed of the plane, and y represents the speed of the wind. Okay, so, and I'm going to put parentheses around because when we multiply these two together, these two will multiply the x and the y. Alright, so let's see what we're going to do next. Well, against the wind. So against the wind, the same trip took 6 hours. So this, by the same trip, we mean the 300 miles, because it's the airplane going 300 miles from west to east, for example, then coming back from the east to the west against the wind. Okay, so against the wind, let's highlight that piece of information that is going to give us the second equation. So the 300 miles. Okay, so and that's going to be 6 hours, but in this case it's x minus y. Alright, so if we set up the system of equations, we are going to set an equation for the with the wind, that is rate times time equals to distance. And then I'm going to set another equation for the against the wind situation, in which rate times time equals distance. So what's this going to be? I know what you're thinking. The next step would be to distribute the 2, distribute the 6, and then remain with huge numbers. So in this case, I'm going to change the game here just a little bit. So what we're going to do is to divide both sides by 2 in this case, and both sides by 6 on the second equation. That's going to give us a new system of equations. Well, actually an equivalent system of equations, in which, well, see how this 2 over 2 cancels and 6 over 6 cancel. 300 divided by 2, that's going to give us 150, and 300 over 6, that's going to give us a 50. And this will be a way friendlier system to work with. And see the coefficients. These are ready to be eliminated for y. We can eliminate the y's right away. Let's set up another system of equations very similar to the with the wind and against the wind, but in this case we're gonna talk about traveling by boat, or on a yacht or something. If you're used to travel by yacht. I haven't, never in my life. But we're gonna run into the same situation. We go through a river, we go downstream, which means with the current, and upstream against the current. So when you have those this type of situations on the homework, you may read either one. So that's why I'm writing both ways to phrase these problems, either using the downstream, upstream vocabulary, or with current and against the current to the corresponding meaning. So a boat travels 180 miles upstream in 20 hours, and it does the return trip, that is downstream, in 15 hours. Find the speed of the boat in still water and the speed of the current. So speed of the boat is going to be Rx, and speed of the current is going to be Y, just the same way for the speed of the plane was X and the speed of the wind was Y. Right? That's how we label them here. So we do that the same. We do the same here. So in this case, downstream with the current, when the boat goes with the current, it's going to go faster and the rates are going to be added. But when it goes against the wind, the boat is going to slow down. So we're going to have a smaller rate, smaller speed. Now it travels a distance of 180 miles in 20 hours. Well, actually, upstream it's minus, yes, that's correct. So 20 hours upstream against the current, and downstream 15 hours. See how it makes sense to have a smaller time for downstream with the current than upstream against the current. So, well, so we're going to use the same idea. Rate times time equals to distance. So we're going to have x plus y times 15 equals the distance 180, and x minus y times 20 equals 180 as well. Alright, and I know what you might be thinking. You're looking at that system of equations and most likely you're starting to hate it because this is what you're gonna do. You're thinking of distributing the 15 to give you 15x plus 15y equals 180. And on the other hand, 20x minus 20y equals 180 as well. If you look at this system, well, look at the numbers. You want to eliminate x. You would have to multiply the number, the top equation by negative 20 and then the second equation by 15. That's going to give you a lot of huge numbers. All right. It may not be the best choice. However, if you want to go this way, I'm just going to wish you good luck. All right, good luck. Have fun. All right, have fun. Enjoy. All right. However, is there an easier way to solve this problem? Well, of course. So in this case, notice 180 is divisible by 15 and by 20 in either case. Okay, so I'm gonna end up with x plus y equals 180 divided by 15. That's gonna be 12, and 180 divided by 20, that's a 9. And if you compare these systems, the one that you might want to have fun with, compare with the easier one, I would definitely go with this one. Okay, so this is way easier. Okay, I would go this way. And the last page, it has to do with mixtures. All right, so a concert sold a total of 170 tickets. Adult tickets were $10, and children's tickets were $7.50. The total money taken, that is the total revenue, is $1,575. The question is, how many of each tickets were sold? All right. So how are we going to set up this problem? Well, so a concert sold for a total of 170 tickets. Notice we have tickets for adults and tickets for children that I'm going to call X for the number of adult tickets and Y for the number of children's tickets. And the total of tickets were 170. Now, the cost per person, well, they were $10 each of the adults tickets, and each of the children's tickets were $7.50. I'm just going to put 7.5. Okay? And the total, well, we're going to find out. All right? The total amount of money is the grand total. So let's see. So to calculate the total revenue, for example, if you sell sodas, for example, for a fundraiser, you are going to multiply the number of sodas that you sold times the price that you sold them. Let's say if each soda is $2, and you multiply by the number of soda that you sold, that will represent 2x. So for example, in this case, the cost per adult ticket is $10 times the number, which we don't know. That's going to be number times cost per person equals the total. That's a 10x. And this times that's a 7.5x, or rather y. And the total amount of money obtained from adult tickets plus children's tickets was $15.75. All right. And then what are we gonna get? So how are we going to set up this system? The first column, x plus y equals 170. And the third column is going to give us the second equation. 10x plus 70y equals 1575. 7.5, not 75. 7.5y equals 1575. And in this case, you might want to do substitution to solve this problem. Alright, let's do another example in here. I'm going to do another one. So, let's see. Burn Steve Jar that is sitting on his piano has 75 coins. So we have a musician at a fancy restaurant playing for the people who's dining in, and people is leaving some tips in a jar. So these 75 coins are all quarters and dimes. And by the end of the first song or the first part of the show, he has $13.35. How many of each type of coin are in the jar? So in this case, we have dimes that are X and quarters that are Y. Value, number times value equals total value, total amount of money. So the value of a dime is 10 cents, but 10 cents is $0.1. And the value for a quarter is 25 cents, which is 0.25 in decimal of a dollar, right? So multiply 0.1 times x, that's 0.1x, and or rather multiplication with a dot to avoid confusions with this x right here, that's a 0.25. Y, the total amount of money 13.35, and the total amount of coins were 75. So the first, just like the previous example, the top and the first column is going to give us the first equation, x plus y equals 75, and the last column is going to give us the second equation, 0.1 x plus 0.25 y equals 1335. All right, so that's the system of equations. If you want me to help you out a little bit more, well, look at the decimal. You don't want decimals, so you have one decimal place, two decimal places, two decimal places. You might want to multiply both sides of the second equation by 100 to get rid of those decimals. So that's going to give us 10x. Oops. The first equation remains the same. The second equation is 10x plus 25 y equals 1335. So x plus y equals 75. And that's the system of equations. And this is the end of this section. So this is a good place to quit. So again, you might want to try this just for fun. Solve this as additional practice. Solve these examples, but here what I'm doing is help you through setting them up, which is typically the hardest part of it, right? So this is the end of this section. I'll see you on the next video.